bigger. That's good. Okay. All right, so where did we end the last time? We had a week break. So we talked about implicit integration, and the best way to solve this is by converting to an optimization problem, right? And when I say optimization problem, I mean minimize some function g of some variable x, and there can be constraints and all these funny things, right? And the g can have different properties. And we talked about a family of methods to solve this. So let me just quickly recap that to bring everybody at the same page, which are called descent methods. That's what's most commonly used in physics-based simulation to solve the integration problems. So the pseudocode is kind of easy. Let me just quickly remind you how that worked. You start with some initial guess or initial estimate of the solution. And the idea is that you progressively get closer and closer to the minimizer of the function g you're trying to minimize. So you have a counter k, and then you have a loop where you repeat the two key things. The first thing is finding a descent direction. So that's a descent direction function, which takes the current state and computes an appropriate descent direction from that state. Second, so this is the finding the descent direction. The second very important part is the line search. Oops, there's too many. Line search, which takes the current state where we currently are, the xk, and the descent direction, and computes alpha, which is just a scalar, which tells us how far do we move. And that's the third step, that's the actual move. So xk plus 1 will be just xk plus alpha d. And then we increment this counter, and this is all repeated until we are converged. All right, so this is a very pseudocode because these things, this finding the descent direction, that's something that needs to be figured out. The line search has to be figured out, and this stopping criterion, that's another like big variable of that algorithm, right? So what we talked about the last time is what is the criterion for a descent, for d to be a descent direction? Do you guys remember that? Not every direction d is a valid descent direction, and there is a simple criterion. You know the function g, right? Usually these things are implemented that you give it a pointer to a function which computes the g and its derivatives. Okay, so when you have like an optimization code, if you are using some library for optimization like knitro or ipopt or some many other packages for optimization, the interface you have is that this all is provided for you, and what you need to provide the optimizer is an implementation of the function g, an implementation of its first and second derivatives, ideally. Okay, and the method and the code will take care of computing the descent directions for you. So yeah, do you remember what was the criterion for when is d a descent direction? Let me ask it this way. So there was this. Okay, so let's we'll recap that. So the criterion for descent direction was the dot product with the gradient at that point, right? So the gradient of the function g at that iterate where the descent direction is being computed, then this transpose d, that means the dot product, and this means needs to be negative. Okay, so that's if this is true, then d is a descent direction. And there is the intuition, right, that the gradient gives you the direction of steepest ascent. So the first order approximation, like approximates the function with a plane. So you want to go against this ascent of that function. Okay, that's the geometric intuition. I talked about it last time, just trying to refresh your memory. Now, if this is the criterion, then the most obvious choice for descent direction, which we were talking about last time, is what? You will remember that? Exactly, yes. It's exactly the negative of the gradient at that point, right? Because unless the gradient is exactly a zero vector, then this is safe to be negative, so this is always a valid descent direction, unless the gradient is zero, at which point you are converged. at which point there is nowhere to go because you found at least a local or at least a critical point. That's a safe statement to make. Okay, so this is what's called gradient descent. If you use the negative gradient, then this method will be called gradient descent, and that's what we talked about the last time. Okay, and the gradient descent is not the greatest method out there, and today we will talk about Newton's method. This is basically an introduction to Newton's method, which can be much more powerful than gradient descent. It doesn't have to. And that's one thing I would like you to take away from this lecture is when is Newton's method necessary and when it's not. Because in like the deep learning and training neural networks, people use gradient descent a lot. So actually in some cases it works fine. It turns out that in most physics-based cases, in most of the situations we deal with in physics-based animation, you actually do want to use Newton's method. Even though there are some recent papers who are kind of toying with the idea of a gradient descent, so it's good to understand the nuances between these things so you pick the right tool for the job. So this was descent direction, and what we'll talk about is basically today are the deficiencies of this negative gradient descent direction and how Newton's method fixes that. Then the next step was the line search, right? So the line search is essentially a one-dimensional optimization problem, okay? Once you have picked the descent direction, the line search answers the question, how far do I want to go from xk in the descent direction d so that I decrease my function as much as possible? That's the question the line search function is trying to answer for you. And that's what we talked about last time, that there is a bunch of different line searches. There are different types needed. They also depend on the types of the descent directions. They differ based on whether the G is convex or not. But I gave you a practical one that's most often used in physics-based animation, and that's the backtracking line search. Okay? If you want to only remember one thing about the line search, the key idea of the line search is this exponential decay kind of idea, okay? That you can start with alpha equals 1, and then you can try to iteratively reduce it by like assigning it alpha equals C alpha, where the C is some constant between 0 and 1. And you try this exponential decay until you get to an alpha such that this xk plus alpha d nicely lowers the value of your objective function. Okay, always keep in mind this is minimization, so what you want to do is find an x such that the g function is as small as possible. That's what we are trying to do, okay? All right, so this is all clear? That's. All right, so why do not we always stick with this gradient descent direction? Why this is not the end of the story? And the reason is sometimes it works well, and sometimes it works horrible, okay? So let me give you an example where it works horrible. And the example is actually so surprisingly simple. So let's take a look at the following optimization problem, okay? So I have a function g of just two variables, x1 and x2, and it looks like this. It's 1/2 of x1 squared plus gamma x2 squared, where this gamma is greater than 0, and that's a parameter, okay? The parameter which I'll vary to demonstrate certain things, okay? Now the task is to minimize, oh, what happened? Just lost the video. Okay, I think it's the cable. So the task is to minimize, works fine. Of course, it's to minimize this function, just a function of two variables, right? Quite simple. This is, of course, just an academic textbook kind of example, right? Because it's kind of immediately obvious what the minimum is, what the solution is. Sometimes the solution is written as like x1 star and x2 star, where the star indicates that's the optimum. In this case, it is easy, right? The first thing you can notice that the function is convex because I made sure this gamma is positive and it's quadratic. And the optimum is super easy to see, right? What is the optimum? 0, yes, exactly. Zeros. And what we're gonna do, we're gonna see how the gradient descent is gonna perform on this optimization problem, okay? So that's also why this is useful, because we know exactly what the solution is, so we can now test how quickly will the gradient descent converge to the solution, okay? Now, because this is just a quadratic function, we can actually work out exact line search, okay? What I was telling you the last time is that exact line search you usually cannot do, because exact line search would mean, oops, that's not what I wanted. I just wanted to go back one. This, yeah. The exact line search would mean find the alpha that gives me the best possible reduction of the objective, okay? Such that the g of xk plus alpha d is as small as possible. The perfect line search, okay? Now, usually you cannot do this, and that's why there are all these like line search algorithms with those funny parameters like the backtracking line search we talked about last time. But in this case, because it's a quadratic function, we actually do have the luxury of being able to compute the exact line search, okay? And I won't bother you with the math, but I will just give you, because that's not my point, you could work it out for homework if you're into that. It's quite simple. You're just minimizing a quadratic function, so it leads to this quadratic polynomial. Everyone can solve it. It just takes a little bit of algebra. And if you do this algebra, then you get this result. So that's those are the results of an exact line search with the gradient descent, okay? So let me write this down. And here is minus gamma minus 1 divided by gamma plus 1 to the power of k, okay? So what I've done here is that we are studying the performance of gradient descent, okay? So the descent direction is always the minus gradient of the function g, okay? And we can do an exact line search here. And after we do a step of exact line search, here is what the iterate will look like, okay? So in this academic toy example, we have the luxury of being able to write a closed form formula for what the iterates will actually look like, okay? In practice, that's usually not going to happen, but for analysis, that's useful. And that's exactly the formula for the iterates, okay? That clear? All right, so now what we're going to do, we're going to, how does this behave? Let's take a look at this. Let's say, for example, to make it a little bit more concrete, let's say what if gamma equals 10? Okay, and I actually have an image that will show you how the gradient descent will work. There you go. Okay, so here for to make the point I want to make, I need to choose a good starting point. So let's say that the initial guess, you know, the initial guess, that's this thing here. That's what you bootstrap the algorithm with, okay? It's kind of important, right? Like if you gave it the initial guess of 0, 0, then the algorithm would be done, right? So if you already give it the solution, then it's kind of moot. Good optimization algorithm should not be too sensitive to the initial guess, right? So here, let's say that the initial guess is as follows, that the x1, I guess 0, right? I could say, and that will be, the first one will be gamma, and the x2, 0 will be just 1, okay? And now let's say you start with this initial guess, then you compute the descent direction, you compute the gradient, you negate it, you compute the exact line search, and if this is your x0, so here is the visualization of the situation for gamma equal 10. Okay, those are some level sets of the objective we are minimizing here. This x0, that's the starting point. Okay, the x1 is 10, as I said here. The gamma is 10 in this example. Maybe let me even write it here. So this image for is gamma equal 10. This is the level set of your objective at that point. And this direction right here, let me grab a different color. this direction right here, that's the steepest descent direction. Okay, that's the negative gradient where it's pointing, right? As you can see, it's perpendicular to the level set here. Okay, like this. So that's what you expect to see. And the exact line search, what it does, it minimizes the function along this line. Okay, there is an infinite line going all this way, and it finds the minimal value of the function g along this line. Okay, and that turns out to be right here. Okay, that's my x1. So that's the first iterate. It also has two components, x1 and x2, of course, and it's right here. Okay. Then I go ahead and do it again, do another iteration, and x2 is here. Okay, it moves over there. Then I do x3, x4, x5, x6, x7, and so on. Okay, and I eventually converge to the right solution, which is 0, 0. So that's fine. The method works. It has to work, right? Because it always decreases the objective. And if you are doing sufficient decrease, then you are guaranteed that it will actually converge to a critical point. In this case, it's even a global optimum. But the point here is that it took quite a few iterations to get there, okay? And this exactly, by the way, this zigzagging path, that's exactly what this minus here means, right? Because what is this gamma minus 1 divided by gamma plus 1? By the way, that's also like why we wrote it in this form, right? This is, look at this thing. That's the same in both expressions. There is a gamma minus 1 divided by gamma plus 1, right? If gamma is 10, then this is 9 over 11, right? And because there is the minus here, that's why this is like flip-flopping, going up and down, up and down, up and down, and so on. Or down and up, down and up. Yeah, right.
Are those perpendicular each time?
Yes.
To one another?
Yes, exactly. Like here, I don't have the level set right at this point, but if I drew the level set, which I can actually attempt that, maybe like here, right? Maybe let's take a look at this guy over here, right? So here would be a level set like this, and this thing would again be perpendicular exactly.
Okay.
Yeah. So it's like if you look at the function restricted to this line, right? If you look only directly there, then you will see some quadratic like this, right? And this is the optimal point. That's the exact line search picks. That's right here. Okay, so it's always perpendicular, always takes the minimum. That's the idea. Probably the most intuitive, most obvious optimization algorithm you can think of, right? Now, here is what the problem is, right? Depending on what the gamma is, this takes a lot of iterations to get to the solution, okay? In this case of the gamma 10, it wasn't that bad, even though it wasn't quite ideal, right? It does this funny zigzagging path, right? Now imagine if gamma was 100, or if gamma was 100, then this factor gamma minus 1 divided by gamma plus 1, how much that is going to be in that case? Well, it will be 99 divided by 101, right? Now, if gamma is 1000, then this fraction will be, of course, 999 divided by 1001, okay? So this is something just slightly below 1, okay? And as you can imagine, the higher the gamma will be, the more zigzaggy the path will get, okay? In other words, this basically reduces the residual based on this coefficient. If this is very close to 1, then it takes forever to iterate to the solution, okay? You can do like thousands of iterations, and you will get like a little bit towards the solution, but you'll still have miles to go, okay? So this is an example where the gradient descent, it works, it converges, but it converges super slowly, okay? And the worst part is that it depends on the problem, on this gamma thing, okay? Yep.
I have a comment about the perpendicular thing.
Uh-huh.
There's no reason they have to be perpendicular. For example, if you start at x1 equals 0 and x2 equals 4, then wouldn't the gradient descent just take you straight down?
Wait a second. What did you say? The x1, 0?
So earlier you commented that all those lines, right, that show the zigzagging pattern are perpendicular to each other.
Oh, not to each other. What I meant that they are perpendicular to the level sets at that point.
That part is true.
Yeah. Yeah, you are totally. They don't have to be perpendicular to each other. Actually, the zigzagging thing and can look like this, right? with higher gammas. So it will be making like very slow progress. We're basically bouncing up and down and making only very tiny progress in the direction you actually want to go. That's the frustrating thing about gradient descent. Okay. Now, it doesn't have to be always so bad, right? I have to choose this x0, this gamma 1 carefully so it behaves like this. Because, for example, what would happen if I said that I pick a different initial point and that x1 will be anything and x2 will be 0. Okay, so I choose a starting point anywhere on the x1 axis. But with x2 0, what would happen in that case? It would work much better. How many iterations would it take to convergence? One, yeah, exactly. Because if I'm lucky with the starting point, the most lucky would be if the starting point already is in the solution, but it doesn't have to be. Even if I am just anywhere on this line, right? Then it turns out that the negative gradient points right to the solution, right? So the exact line search will immediately find it. So it takes just one iteration, okay? Oh, yeah. Forgot my HDMI dongle. Does anybody have an HDMI dongle? So that's why I'm using the VGA, and somehow it's not working so well. That might work. All right, that should be much better. Is it better quality? Can you tell the VGA HDMI quality difference? Cool. All right, where were we? All right, so yeah, sometimes you can get lucky, okay? But that's kind of, you only get kind of lucky if you are on these two lines, right? So either x1 or x2 equals 0. In that case, it just takes one iterations to converge. And so it's not guaranteed it will take forever iterations, but it depends on how lucky you are with your initial guess, right? And if you are unlucky, like in this case, or many other choices are also pretty bad, then the gradient descent can take forever. Now, there are some cases where the gradient descent is fine. Like, notice what happened to the level sets with these higher gammas, okay? This is you can kind of see the squished ellipses, right? If your gamma gets higher, then this is squished even more, right? Then the ellipsis would look something like this, right? That would be squished way more. Oops. Didn't get the ellipse. I'll switch this out. Maybe the level sets would look something like this, right? They would be much more compressed. In phys-space, this actually happens a lot because once you start tweaking like your spring coefficients and so on, then you actually often want to go to some higher numbers like this. Because if you're doing something like a cloth, then you want to make it fairly inextensible. So then you have to crank up this stiffness, like the hook stiffnesses of the springs, right? So you end up with some very large numbers. So that's then indeed then the level sets of the objectives you're optimizing, they can look kind of like this. Okay. Now there are other problems where the level sets are not that bad and they are kind of mostly like spherical, like maybe slightly distorted, not exact circles, but they are kind of spherical. And in those cases, gradient descent actually works quite well because regardless of wherever you start, the descent direction points close to the optimum. So in those cases, gradient descent is actually pretty good. And then there are other pragmatic reasons that Newton's method sometimes can be too high cost to deploy if you are dealing with something like 100 million variables, and this G involves like a million images, like in deep learning. Then Newton's method might be impractical. But then there are other ways to deal with it.
Question.
Anyway, yep.
Sorry, can you expound more on the level what exactly that refers to?
Oh, yeah. Level set means, so the level set is a set where the function has some constant value. Okay, actually, maybe I should write it like this to be super precise. Okay. So that's a set of values x1 and x2 from R2 such that the function g x1, x2 has some constant value c. Okay, where this c is a constant you can tweak. So there is a level set for every c. Okay, here there was some value over here, and this generates in this case it's just a curve like an ellipsoid, and it contains all the points such that the function g gives me the same value. Okay, so here I used it as a visualization tool, basically. You can also imagine it as a height field, as some sort of like bowl, but then like that needs a little bit of, it's kind of hard to draw because then you are drawing like a 3D height field thing. So it's easier to visualize it using the level sets if you are using some sort of like Mathematica, that's what it also uses. Okay, and it really just means a set of points where the function is constant. So the idea here, this c would be kind of high, and it would be getting smaller and smaller the closer you get here, right? There would be some super tiny level sets like around here, right? Make sense?
There's an infinite amount of them for every.
Right. For every c, you have one level set. And it works, of course, not just for two-dimensional things. The function can be any dimensional, and you can still have the level sets. It's a big thing in medical image processing, and the level sets are used a ton. But here is just a visualization tool, just so I can explain this example. All right, any other questions? Okay, so now the question is, we found this serious problem with gradient descent, right? And in practical Gs, we will be optimizing in phys-based when computing like backward Euler or implicit midpoint, all these types of integrators, which is actually what you want to use if you want to be nice and stable. Then we need to be able to solve this more efficiently. And the way to do this is Newton's method, very famous method with some very interesting properties and also some caveats. So let's talk about that. So basically the key idea of Newton's method is to do not a first order approximation like gradient descent. First order meaning looking at the first derivatives. That's what the gradient descent basically does. It just looks at the first derivatives. Okay. Well, Newton says, well, let's look at the second derivatives as well. Okay. Which means that now we are doing a second order approximation of the function. So not just linear, but a quadratic approximation of the function. Maybe I can actually illustrate it, the idea first with a drawing in 1D. Before going into the math. So let's say that the function we are trying to optimize is this. So this is my g. This is my g function. And let's say I have some current iterate somewhere over here. Okay, so let's say that this is my, I don't know, xk. So this is like the one-dimensional optimization problem. That's where I can draw it nicely. Okay. And what you can, one way you can understand Newton's method is by saying that what Newton does, it looks at this point where I currently am. So this is my current iterate xk, and this would be the value of the g xk, right? And what Newton's method does, it constructs a locally optimal quadratic approximation of the function g at this point, okay? So what that means in drawing, it finds such a quadratic function. It's a quadratic function. The original g was not a quadratic function, so it's not the same. Actually, if the g was a quadratic function, this quadratic approximation would be exactly g, okay? But in general, g is arbitrary. So this is only a good approximation in the neighborhood of xk, okay? This is basically the second order Taylor expansion of g at this point, okay? So that's, Newton basically says, well, the original g function is too complicated. Let's replace it at our current iterate, at our current initial guess that we were starting. Let's replace it with a quadratic, and let's minimize that quadratic instead. Okay, so what that means is that you find this minimum over here, right there. and then say that I will move over here. Okay, or say that the difference between these 2 points, that's my descent direction. Okay, that here is where I would like to go, and I can still use line search to find out how far do I want to go in that direction. Okay, in 1D it's kind of silly because there are only 2 directions, to the right and to the left, right? Once it becomes 2D, it's harder to draw, but then there is more descent direction, so that this becomes more interesting. But you can kind of make this picture in your head too, that you have some height field and you locally approximate it with a quadratic bowl, which is a good approximation close to the current iterate. It gets worse and worse the farther you go. And it's still a ball, nice convex ball. If it's not, then Newton actually doesn't work. We will get to that later. But so for now, let's just assume that G is convex, okay? So if G is convex, then this is a nice quadratic bowl, and you can minimize it. And that's exactly how Newton works. So if I'm to write it in terms of formulas, so let's say let me write just x instead of this xk, okay? And so basically what I'll write is a second order Taylor expansion of some function g at point x. Imagine this x is my xk, some arbitrary x, and this p is some like small perturbation. That's the idea. So this will be g of x plus the gradient of g at x transpose the perturbation. So this p is supposed to be something small, okay? Plus 1/2 of p transpose. Now comes the Hessian. That's where it becomes second order. And p, okay? And then there would be some other terms in the Taylor expansion which we ignore, okay? Because we are doing just second order expansion, okay? So this is a quadratic function which is locally optimal approximation of my function at this point x. Okay, that's where the derivatives and the Hessians are evaluated at that point x. That can be our initial guess or our current iterate. Okay, so this goes away, and then what Newton does, it minimizes this quadratic approximation of the function instead. Okay. So to minimize a quadratic function, that's kind of easy, right? Because all we need to do is to take this as a function of p and minimize it over p, okay? Where p is our perturbation kind of thing. Or, yeah. So how do we minimize a quadratic function? Well, that's easy because we just differentiate by p and then set it to 0. Okay, so if I take this and differentiate it by p, then this first guy goes away because there is no p. That's just a constant which disappears upon differentiation. Okay, and so what I am left with will be, and let me also immediately transpose it. So we have column vectors there. So I have the gradient of g at x plus plus the Hessian of g at x times p. Okay. That's just the derivative. It's just easy because it was just quadratic. And then I set this to 0. Okay? Is it clear? Cool. So from this, if I can invert this, then I can easily compute what the p will be, right? Because, or let me do it slowly. It will be like this. P equals minus the gradient of gx, right? And now if I can invert that matrix, this will be minus the inverse of the Hessian times the gradient at x, okay? Sometimes I will just skip this x thing and just rely on us remembering where we are evaluating it. I'll just write it for conciseness like this, okay? Oh yeah, you're right, thanks. There should be the Hessian. Just to make sure we are on the same page regarding the types, this gradient is a column vector. This Hessian is an n by n matrix. This assumes that the matrix is invertible. If G is strongly convex, then it always is invertible. If it's not invertible, then Newton runs into problems, and we'll talk about those later. So let's first assume it's the good case where the G is strongly convex, which means that the Hessian is always positive definite, and therefore I can also invert it. And this is basically Newton's method. Then what Newton says is how do I denote it? Then this P is my descent direction for Newton's descent direction. Okay, this exact P. Now, why this is cool? So let me ask you this: how would this method work on this previous test problem? So if I have the same function to minimize, and now I run Newton's method on it, how many iterations will it need to converge? That's exactly right, yes. Because this already is a quadratic approximation. I'm actually not ignoring here anything. So this actually already computes the exact minimizer of that thing. So regardless of your starting point, regardless of your initial guess, Newton will always converge in one iteration with exact line search here. Okay? So that's the really cool thing about Newton, regardless of what this gamma is. Absolutely doesn't matter what this gamma is. Okay, so that's one of the really cool things of Newton. That's why it's so powerful and used so frequently in physics-based animation, right? Since probably was used even before, but the Baraf-Witkin paper in 1998, they kind of popularized that a lot. And since then, I think basically everybody's using that, except for some special cases where you use actually explicit integration and you do like time adaptation, but that's a different, that goes more to what we talked about before about time integration. All right, so so we saw that on this particular example, Newton works amazing, okay? And if the function is not too far from quadratic, that Newton still works really well, okay? So if I am to draw some more general result, not just for this one particular function where it ended up working super well, we might be like, oh, maybe there's just a special type of function. There is a general result you can say, and that's a fine invariance of Newton's method. Fine invariance. What does this mean? It means that if I have an optimization problem like this, I'm minimizing a function g, I can say, oh, by the way, the x is actually just a coordinate transformation of some other independent variable y. Okay, so here T is a square invertible matrix, square invertible. In other words, the T is just a change of coordinates, okay? Well, if that's the case, then I can as well be minimizing over y, right? I can be minimizing, or I can do this. I can do like a substitution, basically. So let me do it like this. So I can say that I will create some g tilde of y, which will be nothing but my g of t y, okay? And then I can say, well, let's minimize instead over y g tilde y, okay? It's kind of obvious that these problems are equivalent. They only differ by change of coordinates, by substitution, okay? What does this mean is that in the easiest case, when t was diagonal, then you are just basically rescaling your variables, which you can do and will make no difference in the solution because the t is invertible. You will get a different y here, but it's just the t transformation away from the x, okay? The other way you can look at this is from the point of view of this example, the gamma could also be seen as a change of variables, okay? Because I could say, hey, I don't like this gamma here. Let's introduce a variable y, which will be square root of gamma x2, right? I could do that. And this way I convert it to a different optimization problem, okay? Now the cool thing is that if you run Newton's method on this problem, on minimizing the g tilde or y, then it turns out that the Newton descent directions are basically the same. What I mean by basically means they are also related by the t transformation, okay? So let's look into that specifically. If I compute the gradient of g tilde at some point, then it turns out this is just the t transpose of the gradient of g. Okay, that's just chain rule because the g tilde is g of ty. Okay, the transpose there is just because I want to make it a common vector, so I need to multiply from the left. Okay. Now the Hessian does a similar thing. That's also just a chain rule, this time applied twice. So the chain rule on the Hessian looks like this. It will be t transpose, the Hessian of g, the original function, and t again. Okay? And now if we compute the Newton descent direction here, this is also a good exercise to remember what the Newton descent direction looks like. So the Newton descent direction always is a minus. Now is the Hessian now of g tilde, okay? Inverted Hessian, and then there is a gradient of g tilde at some point. Okay. Now if I just plug in these expressions, okay, I will see that this is minus the so this will be t inverse. Now will be the Hessian of g, and there will be t inverse transpose, but the Hessian right, so minus t, okay, inverse transpose. And this was the t transpose times the gradient of g, okay? Now this is of course associative, so these things cancel out. So this will be just minus t inverse the Hessian of g, this was supposed to be inverse, gradient of g. Okay, so if I say this was some delta x, like a Newton descent direction for the original problem, and this was some delta y, the Newton descent direction for the problem after change of variables, okay, what I see immediately is that, let me just rewrite it for clarity, so this is minus delta y equals minus t inverse delta x, right? Well, I can also write this as delta x equals t delta y, just to tidy it up a little bit, right? That's obviously equivalent. So that what this means is that the Newton descent direction for the original problem with the x is related to the Newton descent direction for the problem after change of variable, the delta y, just by the transformation t, okay? And that's what the affine invariance means, okay? The Newton descent direction doesn't change up to the change of variables, okay? And it's basically just a long way of saying that Newton's method is unaffected by change of coordinates, okay? So it's not just this particular case with this funny gamma, but in any case you just do an affine change of coordinates, Newton method will produce the exact same descent directions up to the change of coordinates, okay? So in other words, if it works well in one set of coordinates, it will work equally well in another set of coordinates, assuming that your aligned search is deterministic, okay? Here is another cool thing about Newton's method, and that's called Newton decrement. Yeah, let me do another page. This is another advantage of Newton compared to gradient descent. Basically, if I was to first say it in English before writing down formulas, if you have a gradient, if you are doing gradient descent, you don't have a clue how far you need to go. You don't have any hint for the line search where the optimal solution could be. Okay, you are only like looking like at it like super locally. And you only know the direction to go, but you have no clue how far to go. And you rely completely on the line search to give you a good distance to go in that distant direction, okay? Now with Newton, you actually are in a better situation. If you look at this picture, it's kind of clear, right? Because the Newton actually already gives you a pretty good estimate how far you need to go, right? Because the Newton is not doing just a first order approximation. The first order approximation, that would be a line, right? That would be a line that would look like this. That's essentially what gradient descent is using, right? Well, minimizing this line makes absolutely no sense, right? Because you can always make it as small as possible. So it's actually a poor approximation of your original function the further you go. If you go far, it's a poor approximation. Well, the quadratic approximation is much better because it has some well-defined minimum. And that's also a very good starting point or initial guess for the descent, for the line search, if you will. Let me repeat it. Initial guess for the line search. It's a good initial guess for the line search, okay? So that's another way how Newton's method is good. And it's also very useful as a stopping criterion, okay? There's this, remember that in the pseudocode, there's this funny thing until converged, right? And we kind of hand waved our way around it the last time. We said you can look at the magnitude of the gradient or something like this. But for Newton's method, there is a slightly better stopping criterion, which is related to the Newton decrement. So what the Newton decrement is, and the best way to show this is here, is how much the quadratic approximation will decrease if I take the full Newton step. Okay, by full Newton step, I mean right here, go to the minimum of the quadratic approximation, and then the Newton decrement is nothing but exactly this distance, okay? Newton decrement, that's this, okay? So basically what that tells you is how much of an opportunity for decrease of the original function there is. If you assume that the quadratic function is a good model, good approximation of your original function, this tells you whether the Newton step can expect to do a sufficient decrease of your function, okay? So if you are to compute it, then what we need to do is to do what? So we have the Newton descent direction first, so that's the delta x, and that's the minus the Hessian of the function g. Again, it's at some point xk, okay? I'll not write it everywhere because that would just mess up the equation. Just remember this is all evaluated at some point. So this is the Newton descent direction. And what we can take a look at is we have this quadratic approximation here, right? And what I can do, I can just plug the delta x in here. Okay, instead of p, I will just plug there the delta x. Okay, in this drawing, by the way, the delta x is exactly this. Okay, this would be the delta x. This is my Newton descent direction. So I can plug it in here and then see how much it actually reduces the value of the objective from here to here. Okay, so let's do that. So what I will do, I will copy this, and instead of p, I will put there delta x. Okay, so let me do this quickly. So this will be g of x plus the gradient of g. You know what? Let me even ditch the x's. No need for those x's. So this is g plus the gradient of g transpose. So I put there delta x. Okay. Plus 1/2 of delta x transposed, Hessian, and delta x again, okay? Now I know what the delta x is. The delta x is this. So the next step is to plug in the value of the delta x. Okay, so let's do this. So the g I will just copy, and this is the gradient of g. So now the delta x is, and I'll erase this, now that's minus, right? Because the delta x is, now it's minus the Hessian inverse gradient. Okay, so I took this delta x and I replaced it with this, and I got that. I hope I got it right. All right, and the second part is even a little bit more funny. So I have the, oh yeah, so what I'm gonna do, I'm gonna plug their distinct transpose. So I get the, so that will be, I have two minuses there, so they will cancel, so I can keep the plus there, that's fine. But here I have the gradient g transposed, and here I have the Hessian g inverse transposed. Then I still have the original Hessian there, this one, okay, so it's still there, the Hessian of g. And then I have another delta x, okay, so that means another Hessian g inverted this time, times the gradient of g, okay? So it's lots of funny terms. But the good thing is that you can probably see this will cancel, right? And the inverse transpose, the transpose of the Hessian doesn't matter because the Hessian is symmetric, okay? So this is still, this will be just This is the same as just the inverse, okay? Because the transpose doesn't matter because it's symmetric. So if you put this, okay, let me do it in steps. So this actually reduces to 1/2 of gradient G transpose. Now comes the inverse Hessian. And this, okay? Does that sound correct? I think so. Now the funny thing is that's the same as this first term here, so I can further simplify this, okay? Any questions? No? Okay, so this is -1 this is plus 1/2, so I can actually put these together, right? So if I put them together, this will be G, and if it's -1 plus 1/2, that's -1/2 of this thing, the gradient transpose, the Hessian inverse, and the gradient. Okay, and voila, this thing is lambda squared, where the lambda is called the Newton decrement. Or maybe the whole thing squared could be called the Newton decrement. Because here you can see this is exactly how, if you take the full Newton step, meaning if your alpha in line search is 1, okay? If you take the entire, if you step over the entire descent direction in this algorithm, if the alpha wasn't there, if the alpha was 1, so that means you are taking the full step, okay? If the d is the delta x, the Newton descent direction, if you take the whole descent direction, then your objective reduces by this amount, right? The g was the original value of the objective. Maybe now I could write like this g meant g at xk, right? When xk is my current iterate. All these gradients and Hessians are also evaluated at xk, okay? So this tells me how much the quadratic model would decrease if I take the full Newton step, okay? And that turns out that's a very good stopping criterion for Newton's method. And the stopping criterion, or the convergence criterion, then is simply the lambda square half. That's exactly what you have here, is smaller than epsilon. Meaning, if the quadratic model is kind of flat, that even if you go to the minimum of the quadratic model and you don't get too much of a decrease, you might as well call it quits. That's kind of the idea. There is a theoretical motivation behind the stopping criterion too, and that is, again, a fine invariance, because it turns out that if you do, again, just a change of coordinates like we did here, it actually turns out the Newton decrement doesn't change at all. Okay, the Newton decrement is also a fine invariant. And that's important then for convergence analysis of the Newton's method to like be able to prove some theoretical properties of that. But it's also a practical stopping criterion. Are you guys using it in your Newton's implementation? Some of you was implementing that. You can use simpler ones too. You can also say the number of iterations is 20 or 10. That you can do too. What Boraf and Witkin did, they said the number of Newton iterations is actually 1. The Newton is so powerful that even 1 iteration does some good job already. But if you want to properly minimize it, then you do it this way. So let's take a look at the convergence analysis quickly. I just want to give you the digest of this, because this can be studied for probably an entire semester. I just want to give you an idea how it works in practice, okay? And there are also some pretty cool theoretical results about the convergence of Newton. So I will mention one of these theoretical results, which is the classical convergence analysis due to Kantorovich. And the assumptions are as follows. So first we assume that G is strongly convex. That means that the Hessian at every point will be positive definite, so we don't have to worry about not being able to invert it. It means it's always invertible. And we don't have to worry about any non-convexity, obviously. And second, and that's an important assumption that's good to understand, is actually that the Hessian of G is Lipschitz continuous. Which means this. That means there exists a Lipschitz constant L that's just a scalar, and I make it a non-negative, such that for every x and y, following is true. The norm of the difference of the Hessians at x and y is bounded, this was the norm, is bounded by this L, the Lipschitz constant, times the norm between x and y. Okay? So before we proceed, maybe let's clarify what this means, because it might not be immediately obvious. The Lipschitz continuity. So this is Lipschitz continuity of the Hessian of the function, okay? So this is some sort of assumption of well-behavedness of the function g, okay? What this really is, you could imagine you divide this by the norm of x minus y, okay? So imagine you just divide this by x over y, and then this kind of looks like taking yet another derivative, okay? So what this really is, it's a bound on the third derivative of g. Okay. And intuitively, you can understand it as saying that this L quantifies how well is the G approximatable by a quadratic function. Okay. And that's important for the intuition of understanding when the Newton's method will behave well, right? Newton's method will behave well if your G function can be well approximated by a quadratic function, right? If the quadratic approximation is poor, which can actually happen, then you can expect Newton's method to work poorly, okay? So this is a mathematical way of quantifying this poorness, okay? That this L tells you how quadratic the function g is, okay? What if L was 0? What if I have the Hessian is Lipschitz continuous with Lipschitz constant L equals 0? What does that mean? That's a very special case, right? That means the function must be quadratic because the thing on the right will be 0. So that means that the Hessians between x and y must not change at all. They must be exactly the same. And the only function that has the constant Hessian everywhere is a quadratic function. Okay, so if L was 0, then this implies that G is quadratic. Okay, if it's non-zero, then it measures how non-quadratic it is. Okay, so that's kind of the cool thing. So then the lemma due to Kantorovich, the classical convergence analysis of Newton's method, says that if these two assumptions are satisfied, then there exists a constant eta greater than 0 and some constant gamma also greater than 0, such that, and there are two claims there, if the norm of the gradient of g is less than this eta thing, then the value, and now we are getting to the meat of the theorem, okay, the thing that actually matters, then we have a guaranteed decrease of the objective function minus gamma. That's the guaranteed decrease, okay? Then the second case, if this is not the case, if this, oh, sorry, I got this wrong. This was supposed to be greater or equal than eta. If it's less than or equal than eta, then even more interesting thing happens. Then the norm of the gradient of g at xk plus 1 must be less than or equal c times the norm of the gradient at the previous iterate squared. That's really the main thing there. All right. So the lemma says if if these assumptions are satisfied, then the eta and gamma exist such that, and those are basically two phases of Newton's method. Okay, the first case that's sometimes called the damped Newton phase. And it's called damped because here in general you need to use the backtracking line search or some other line search, okay? The second phase is called the quadratic convergence phase or the quadratic phase. Sometimes they also just call it phase 1 and phase 2. Phase 1 and phase 2. Okay? In the first phase, you are guaranteed that after you take the Newton step, your objective will decrease at least by gamma. Okay? You don't know what gamma is, but this lemma guarantees that it exists and is greater than 0. Okay? So this guarantees that Newton will keep decreasing the thing. And eventually, what happens is that this gradient becomes small enough, and then the quadratic convergence kicks in, okay? And what that means, this is something pretty cool. If you look at this, that means that the norm of the gradient up to some constant will be less than or equal than the norm of the gradient squared. Now assume the norm of the gradient needs to be something small. So assume that's something like kind of tiny, right? Like 10 to minus 3 or something like this, okay? If this is small, then squaring this is super small, okay? Squared small. And that's what the quadratic convergence means. Loosely speaking, you can say that the number of accurate digits doubles every iteration, okay? The other characteristic of the second phase is that line search is no longer needed because you are always taking full Newton steps. So the optimal alpha is always 1. Okay? So you always go to the minimum. You take the whole Newton decrement, you always go to the minimum of the quadratic approximation. Okay? So I won't give you a proof of this. That would take a whole another lecture. If you wanna look at this, then I recommend Boyd's Convex Optimization. That's a free book online, where you can see this analysis and also more fancy analysis using self-concordant functions. That's even more advanced theory of convergence of Newton's method than this classical one. Okay, but what I want to show you, what does this actually mean in practice? Because this is not just a theoretical result. This has very significant practical implications. If you look at a typical error plot, convergence plot of Newton's method, okay, so here on the y-axis I will plot the error, actually the logarithm of the error, okay, so log error, where the error is measured simply as the value where I currently have at my gxk, okay, minus, you know what, let me do this on another page because I'm short on space here. Do it nicely. So here is log error. And how do I measure error? Well, error simply is the value of the function I currently have minus the value at the optimum, x star. Okay, I would like to bring this to 0, obviously. Eventually, I would like my xk to get to x star. X star is the optimum. That's where I want to get. If I'm strongly convex, then there is just a single point. There's no funny business with like multiple and so on. Okay. All right, so this is a convergence plot. And if you run this on some minimization problem with Newton's method, with backtracking line search, the curve you will get looks usually something like this. Okay, so that means here are my iterate. This would be my x0. So this would be this here would be like some x. No, on this axis I have actually the number of iterations. Okay. This would be my initial error, so something large, like 10,000 or something like this, okay? Then I do another iteration, the error keeps decreasing, okay? I keep iterating. Let's say that, I don't know, this is like, just to give you a sense of scale, 5, 10, 15, okay, and he would be like 20. Just to give you a rough idea, okay? Those things are to be taken with a grain of salt, but this is, the order is about right, okay? So those are my iterates, and what I wanted to show you is that this is, if you have correctly implemented Newton's method, this is what you should see, okay? Or maybe I can draw the divider here. This is the phase 1. This is the phase 2, okay? So in first phase, what you see is this like constant decrease. It just keeps decreasing little by little by this gamma, okay? That's exactly what this first class has. That's the damped Newton phase. And also in general, the backtracking line sort actually does something. Okay, it sometimes reduces the alpha to something smaller than 1. Okay, and in the second phase, and that's the cool part of Newton, that's when the quadratic convergence kicks in. Then we are in this regime. Okay, and in this case, the convergence plot tips over and it very quickly drives the error to 0. Okay, you might have heard that once you are close to the solution, and this is what quantifies the close to the solution, where the gradient of g is less than some constant, then the convergence of Newton is super fast. Okay, because it essentially doubles the number of accurate digits every iteration, because you only have that many digits in your floating point, either float or double, then basically you can say that this is at most 6 iterations. Okay, and that's when you want to be, if you want to be like really precise. Okay, it doesn't make sense in this second phase to be doing more than 6 iterations. Okay, which is also why the stopping criterion for Newton, if everything is working well, is kind of moot, because once you get to this phase, it doesn't really take too many iterations to get to like a super accurate solution. Okay, to have like all your 15 decimal digits or whatever is available in your floating point, to get them all right, that just takes a few iterations. Okay. Probably the most important thing is that the graph looks kind of like this no matter how many variables the g has. Okay, I showed you the toy example where g had 2 variables, where for sure everything's going to work very beautifully there. Okay, in the quadratic case that would be just 1 iteration, would be all over, right? But the cool thing is that even if you have millions of variables, this graph basically doesn't change. Okay, so as a rule of thumb, if things are working well, if everything is implemented correctly, you don't have too much numerical errors in your derivatives, and this Lipschitz constant L is not too high, then you can expect to get super accurate solution in like 20 iterations or so. Okay. Now, it doesn't always have to work. There are cases when this breaks down. The first case, that's what I kind of mentioned already. If this L was for some reason large, okay, then what can happen? You tell me. What can happen is that the damped Newton phase, this first phase, can take forever, because then this gamma can be small. Okay, so before you get to this quadratic convergent regime, you might need to do millions of iterations. So that would not be great. Okay, and that happens in the case when the quadratic approximation is not a good approximation of your function. Okay, in optimization, this usually happens for some, if you put some function like minus log x, which is strongly convex for x greater than 0, okay, but then it looks something like this. Something like that. But once you are in this crazy regime that is this asymptote at 0, because then this of course goes to infinity, then the quadratic approximation is not really that good, because the function is highly nonlinear, so the quadratic approximation is poor, and Newton's method will perform poorly in this case. Okay, it's a pretty contrived example, but these functions are actually used in optimization, and then there are more fancy methods in optimization to deal with those. They are called homotopy or continuation methods. Okay, or interior point methods. If you go to study constraint optimization, this is what comes up. Okay. So that's one problem that can happen with Newton's method. It usually won't happen to you in physics-based simulation unless you go to some crazy barrier functions like this. This is sometimes called a barrier function because it erects this barrier by 0, which the energy cannot pass. We will see this when we'll talk about the Nell-Hookean model. It has exactly this barrier term in it, and you can expect Newton's method without further precautions to choke. Okay. The other case where Newton fails is when this assumption of strong convexity is violated. And that's actually the more practical problem you have to deal with in physics-based animation, because even simple mass spring system can very easily be non-convex. Okay, so not only we lose strong convexity, but we even lose the very basic convexity. Okay, and in that case, Newton fails. How does it fail in that case? in the case before, when I said it's like minus log x, then it fails by this L being very high, consequently gamma being very small, so this first step taking forever. If G is not convex, how does Newton fail? Or can fail?
Wouldn't it not correctly obtain the correct minimum? When you take that first derivative as 0, there could be you could find a local minimum instead of the global?
Yes. Yes, that's one aspect of that. That's right. If you look at this, right, we'll talk about it in more detail next time because I want to explain this properly. How that's basically so far what I covered is essentially convex optimization. Okay, this all works in case the G is convex. If G is non-convex, you have to take some precautions so these things still work. Okay, so I still have a few minutes, so let me just explain you what can go wrong if G is non-convex. Okay, so just by looking at this, immediately what can go wrong, this inverse does not have to exist. Okay, if you are, and that's kind of intuitive, right? Like if even I can show this even in the 1D example, right? What if my function looked like, what if my function was a line and then it curved, okay? And let's say that here in this region was a perfect flat line, okay? Well, what happens if I try to compute Newton at this point? Well, the optimal quadratic approximation of a line is a line. You cannot possibly improve that, right? That means that the second derivatives are 0, okay? That means that your Hessian is not invertible, okay? That means that you cannot compute this. Worse, it can be something where the Hessian is invertible, but it's poorly conditioned. So the eigenvalues of the Hessian would be non-negative, but there would be some tiny numbers. Okay, that also gets pretty bad because that means that you are doing a crazy scaling of the gradient. So that's also not good. Like basically, if this was almost a line, then Newton would also work terribly. Okay, and even worse, it will be if you have some concave dip, then Newton completely fails. Then you actually are able to compute this inverse. If the matrix is indefinite, if the Hessian is indefinite, you can invert it. You can only not invert it if it has 0 eigenvalues, right? Because you cannot invert 0. If there are negative numbers, you can still invert those, but the descent direction you get is actually not a descent direction. You can get an ascent direction. So that's a problem because then your algorithm wouldn't work at all. So you have to deal with this. And that's what we will discuss next time, how to deal with this and how you can write a solver that actually is able to robustly solve even the non-convex energies like mass Planck systems and finite element method energies. Okay. So that's all I wanted to tell you today. Any questions? Cool.